I think we can get started now. Hey guys, welcome to lecture number 6. This will be the last lecture from chapter number 2. And today we will talk about exponentials and logarithms. And that's why we left these two functions a little bit, because they're very special. And you will see why these functions are special. When we will talk about the limits of functions, you will see that, for example, the exponentials will be involved with some limits involving this famous number e. So we will be talking about that. But before we talk about these limits, I would like to state the main properties of the exponentials and logarithms. And you will see one thing about these two functions, that the exponential function and the logarithm function, they're inverses one to another. So if you take the exponential function, and if you like to find the inverse of the exponential function, that would be the logarithm, and the other way around as well. All right, let's get started. So let me start first with the exponential function. And well, the exponential function is probably, as you know by now, it will be, will be defined in the following way. So that's the exponential function. As you can see, it is defined as the function which takes all the values x to b of x, b to the power x, sorry. So f of x is b to the power x for b positive, and of course it has to be different than 1, because if it's 1, then the function is 1, so there is nothing to talk about. Well, let me, so this would be what we'll call the base. And this is what we will call the exponent. Right? And there are plenty of examples here. If you, for example, let's just take f of x to be 2 to the power x, right? So in this case, b equals 2. So this is what we call an exponential function. Or another example, if you want, f of x will be e to the power x, whatever it is. We will call this the basis of the natural logarithm. Anyway, we'll get there. Or if you want another example, f of x can be 1 over, well, since we're talking about, let's not put something less than 1. Let's say 2021 to the power x. Again, this is an exponential function as well. Well, if you look at this exponential function, right, there is no way, well, actually, this is positive. I can cook up another example. Let's say 1 over 1000 to the power x. You see, it's something between 0 and 1 here. So it's very small, but as you can see from these examples, no matter what the base is, as long as it satisfies the conditions that b is positive and not 1, but even if b is 1, so in any case, b to the power x will always be non-negative, so always. Anyway, for x large enough, as x approaches infinity, and if b is between 0 and 1, it will be something like 0. But in any case, for x real, b to the power x will always be non-negative. So we can write in positive. In fact, we can write that f is defined. So f is defined in this way. defined on R, right? And so the domain is R and the range is 0, infinity. So that's what we need to know. Will always be positive. Well, so any number you take in the range will be positive. But also, you'll see when we'll define the logarithm function, you'll see that the domain will be 0, infinity. So we will switch the two. All right. So that's the exponential function. And now let's see how the graph of the exponential function would look like. As you can see, something happens when b is greater than 1, and something else happens when b is between 0 and 1. All right, now, can you tell me, if you look by just looking at the graph, do you see something in particular? What do you see? What is the main the first observation that by just looking at the graph, the two graphs?
They're flipped.
It flips, right? But before we even go there, is there a certain point that the graph passes through by just looking at it? So keep in mind that f of x, 0, 1, like Josh says. So just look at this guy. So once again, f of x is b to the power x, and we know that b is positive and b is different than 1. Well, if you take x to be 0, you will see that f of 0 is 1. So the points, right, of coordinates 0, 1, so the point, let's just say m of coordinates 0, 1 is on the graph of f, of our function f. So if you look here, all right, you see this point here and this guy here, by just looking at them, so I see a question here. Let's see. So what did you say the range, the domain of? So the domain is R, right? You can take, and the range will be 0, infinity, right? Will always be like this defined. So that's how we're going to define an exponential function, right? So you see this point here of coordinates 0, 1 is always going to be on the graph, no matter on the exponential, no matter how you define the exponential. As you can see, even for this case, when b greater than 1, or for this case, when b is between 0 and 1, the point of coordinates 0, 1 will always be on the graph of f. Now, exactly. So anything raised to the power 0 is 1, correct? Yes. Anything finite except 0, right? Because you will see 0 to the power 0, which will be undefined. So any finite number raised to the power 0 will be 1. You will see that 0 to the power 0 or infinity to the power 0 will be undefined. So we will have an indeterminate, and we'll have to compute. Basically, it's going to be like a limit. But anyway, we'll go there, and you'll see exactly how we will compute this. Well, now let's just look again at the graph of the two graphs, right? So you said, somebody said something else here. Let's see. What did you guys say? What do you see? Other thing that you see in these two graphs? Oh no, just like looking intuitively. Don't talk asymptote. You're going way way beyond the material that we have seen so far. They mirror each other. You see someone, so they flip. Just look at let's look at the first one. What can you tell me about the first one? If you look at the first one.
Keeps going up.
It keeps going up. Okay, that's a very good observation. So let's see, this is going up. It keeps going up. Let me write it this way. So the first graph keeps going up. What about the second one? What can you tell me about the second one? It goes down, so it keeps going down. And what do you think? Do you think it will touch the x-axis?
No.
No, it doesn't touch the x-axis unless x is extremely large, like infinity. Keep that in mind, right? Or negative infinity. In the first part, you see it's coming from the negative sign and it goes up. So probably at negative infinity, it will touch 0, but only at negative infinity. So there is no way any of these two graphs will touch 0 at a finite number. And also if you look at the second graph, it will go very, 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 very close to the x-axis, but it will not touch it in finite time. So it only for x, when x goes to infinity, it will touch it. So that's what you have to know about the graphs of the exponential function, right? So keep these in mind. Now let's see some properties. Let's see, these are the properties of the exponentials. And I would like you to look very close at them. You see, the first one, probably you know it from pre-calc as well. So the first one is that b to the power x times b to the power y is b to the power x plus y. So in other words, you have the same base. So when you multiply two exponentials with the same base, the base will stay the same and you add the exponents. So multiplication between two exponentials with the same base and different exponents will give you the exponential with the same base, but you add the exponents. The same thing goes when you divide the two, right? When b to the power x over b to the power y is b to the power x minus y. So in this case, you divide two exponentials with the same base, right? And the result that you will get is that this will be b, the base will stay the same, and you will subtract the exponents. So that's what you're gonna do, right? And of course, here when you raise to the power an exponential to another power, so you have something like b to the x, everything to the power y, this will be b to the power x times y. So the base will stay the same, and the exponents, you'll multiply the exponents, right? So let me just give you an example of, if you have something like 2 to the 3, right? Or maybe not, maybe we should use some x. So let's see examples. So let's see, 2 to the power x times 2 to the power x plus 3, right? As you can see here, we have the same base. So we'll keep the base the same. So it will be 2. And here we will add the exponents. So it will be x plus 3, which will give us 2 to the power 2x plus 3, right? Now let's see for the second one, what if we have something like this, 2 to the power x plus 3 over 2 to the x. So as you can see, I'm dividing two exponentials with the same base, but with different exponents. So this would be 2 to the power x plus 3 minus x, which will give us x plus 3 minus x will be 2 to the power 3, which is 8, right? So this is how you operate with these. And let's see for the third one, let's take something the same, 2 to the power x, everything to the power x plus 3. So this would give us, as you can see, I'm raising to the power the exponential function to the x, everything, I'm raising everything to some other power. As you can see, the base will stay the same, and in this case, I'll multiply the exponent, so this would be 2 to the power x times x plus 3. And if you want, you can do some computations here. So it will be 2 to the power x squared plus 3x. So these are the main properties for the exponentials. I'd like you to keep these in mind. They're very important. I would like you to look at them one more time. Right, they're very easy to remember. Okay. Any questions so far? Is everything clear? Or okay, there are no questions. Now I'd like to talk about the logarithmic function. So, like I said, if we have an inverse function, there will always going to be, if we have the exponential, function, there are always going to be the inverse of the exponentials of the exponential function, which will be given by the logarithm function, as you can see. Well, since y equals b to the x is 1 to 1, so pay attention to this fact. We said what 1 to 1 is at the beginning. So since this is 1 to 1, we must have an inverse. And the inverse, guess what, is given by this. So this is what we call the logarithm function. So this is nothing else than the logarithm of x to the base b. And the way it works is like this. As you can see, b to the power log b, log in base b, we can write it like this, of x, it will be x. Or you can also swap the two, right? But it's the same. So it's log in base b of b to the power x, right? So let me put it this way. This is a nice way of putting it, right? So their inverse is one to another. So this function, let's say f of x log in base b of x, right, will be defined in the following way. So it will be defined as from 0 infinity and real value. As you can see, the domain is 0 infinity and the range is r. So that's the logarithm function. So that's right here, logarithm function. And if you want, you can write in that, okay, let me write somewhere here, that f inverse of x is, will be the exponential function. So it will be b to the x, right? So the inverse of the logarithm is the exponential function. As we have said. And also the other way around, the inverse of the exponential function will be the logarithm function. So that's what you need to know, this function. Log in base b of x if you want. Right? Okay, now let's see some properties of the logarithm. As we have seen properties of the exponentials, why not see properties of the logarithm? And look at them closely now. You see, the exponential, let me go back a bit to the exponential and explain it a bit. It says that it will take you the product and will try, remember when we had, let me tell you this. So the exponential, remember it was b to the x times b to the y. So it will take a product and will transform it into a sum. But now here, regarding the logarithm, it will be the other way around. It will take you, look here, it will take you the sum when you add two logarithms, log in base b of x plus log in base b of y. So it will take the sum and it will transform it into a product. So it will be log in base b of x times y. So keep that in mind. That's why I'm saying that they're inverse one to another. Also think of the operation. So if the exponential takes you the product, puts it into a sum, think that logarithm will be the other way. It will take you the sum and put it into a product, right? So always remember them like this. Try not to remember them by heart, just by also by their properties and how they behave, right? Anyway, we'll see examples. Let me erase this here because I want to give some examples as well. Also, the second property, if you look at it, is that log in base b of x over y, right? As you can see, I'm taking the quotient here of the two numbers. Guess what? It will take the quotient and it will transform it into, you subtract the things, right? So log in base b of x over y will be log in base b of x minus log in base b of y, right? That's quite expected. So, right, you have something like this here. Well, the third property, when you have something log in base b of, and you have a power, right, inside the log, guess what? The power will go outside. So you'll take this guy, put it here in front of the logarithm, as you can see it here. So it will be y times log in base b of x. And of course, if you log in base, in any base of the quantity 1 will be 0, and log of b of the same thing will be 1, right? Imagine here, if you apply the previous rule, this you have 1 here, it will be, that's it. Or anyway, you just, no, it doesn't matter. So these are the properties of the logarithms, and they will work in any base. We will see that there are some special logarithms. For example, when we have logarithm in base 10, in base e, and so on. And you will see what do I mean by base e. We will talk about that this lecture. Let's see some examples. So let's see here. For example, let me go with the first. If we have log in base 2 of x plus log in base 2 of x plus 3, right? This will be equal, according to the rule, is log in base 2. So we'll keep the same base of the logarithm and we will multiply the x times x plus 3. Which will give us log in base 2 if you want, do the computations, x squared plus 3x, right? So that's how we are going to operate. Now let's see the second one. if we have something log in base 2 of x plus 3 minus log in base 2 of x, this will be nothing else than a log in, according to the rule, log in base 2 of x plus 3 over x. As you can see, I applied the other way around, right? So I'm going from right to left. Or if you want, this will be log in base 2 of 1 plus 3 over x, if you want to write it like this. Let me just, so this is the first one here, and this is here. And now let's see another example here. The third one is we have log in base 2 of 2 to the x, if you want, right? Which will be, or maybe I should put 2 to the power x plus 3 so that I can make it look a bit fancy. So this is 3 here. As you can see, this will be the power, right, is x plus 3. So in our case, y will be x plus 3. So it will go outside the logarithm. So it will be x plus 3 times log in base 2 of 2. And how much is log in base 2 of 2? Can you tell me based on the rules below? What is it? 1, right? So this guy here is 1, according to this here, right? As you can see. So this would be nothing else than just x plus 3. X plus 3 times 1, which is x plus 3. That's the result. Anyway, in your homework, you'll see plenty of other examples on how to operate with exponentials and logarithms. But these are the main properties of the logarithms. So keep this in mind. So in the same way, we have the main properties of the exponential function. The same thing will happen for the logarithm function. This is how you operate with both of them. Anyway, there will be examples when you will have to operate with both of them at the same time. Anyway, we'll get there. But these are the main properties. I want you to have a good look at them one more time before we go further. All right. Now let me talk about the graph of the logarithm, and I would like to compare this with the exponential function. Can you tell me by just looking at the two graphs, what are the similarities? What is the difference between the two? You see, if you draw here, what did we say about the graph of f and the graph of the inverse? So they're symmetric with respect to the line y equals x, right? So if you draw the line here, let me just, that goes through the origin, and the same thing I'll do here. Although the graph is scaled, well, it doesn't look that way, but they're symmetric with respect to y equals x. So that's what you need to know, right? So they'll go through here. Well, they don't look quite like lines, but anyway, these are lines. Let me just say so that the same thing will go for this one. Both of these two are lines. So as you can see, so this is one of the main property. But what can you tell me about? Well, we've talked about the exponential function. Now, I would like you to look, you see the picture below is the graph of the logarithm in base b of x when the base is greater than 1. What can you tell me by just looking at the graph? Can you tell me something? You see, if you compare the two graphs, so the exponential graph has something to do with the x-axis. The the graph of the logarithm will have something to do with the y-axis. So what can you tell me by just looking at the picture? What do you think is happening? Asymptote, but anyway, we haven't talked about that, so just say it without the word. It won't touch it, right? Get super close. Will it touch the y-axis? Not quite, never infinite time, right? But it will get very, very close. Yes, that's correct. It will get very close, yes. What else can you do? Yes, at infinity, correct. It will, yes, for the limits, when we'll talk about this, yeah, it will touch 0, but not infinite time, exactly. Yes, Jonathan is right. What else? What can we see? By just looking at the graph. Come on, don't be shy. So do you think the graph is rising? Is by looking at it? It is increasing, correct. So it's rising. As you can see, it goes from negative infinity on the y-axis and it will keep going. So the function will be what we will call increasing. Yeah, that's a good observation, right? All right. So these are the two, the main properties. We'll see more, but just keep in mind the graph of these two functions, of the exponential and logarithm. All right. Now I'm going to talk about something. Since we talked about limits, I want to go back, go to something special, and I would like to turn your attention to this base e. So e is the base of the natural log. So let me write here the base of the natural log logarithm. So that's what you need to know about this. So this is this number e, the base of the natural logarithm. And what we also say is that these things happen. And first, let me refer this to the limit. So e can be expressed as the limit as x approaches 0 of 1 plus x, everything to the power 1 over x. But also can be expressed as the limit when x approaches infinity. And we haven't learned about limits at infinity yet. We will learn, but I just want to divulge this beforehand so that you know. So like I said, is the limit as x approaches infinity of 1 plus 1 over x, everything to the power x. So that's what you need to know with this. This is very, very important. So this is right. But also you can see the base of the natural log, right? Just like I said, ln of x, the notation will be ln of x. Or sometimes I saw this notation as well, log x, log of x. It doesn't matter, but usually in this class, I think we'll stick to ln of x so that things will be clearer, so that you would not mess for log in base 10, but anyway. So ln of x will be nothing else than logarithm in base e of x. So keep that in mind from now on. You see, this e is this special number, this very mysterious number. It's approximately 2.71 and so on. It's an irrational number. It's not a rational number, cannot be expressed as a fraction. Anyway, it's an alien, I would say. It's even more than irrational. It's what we call transcendental. Anyway, it's like an alien number, just like pi. And you cannot name too many of them, but there are plenty of them, as you can imagine. But one of the most well-known, I mean, the most well-known aliens are E and pi. Pi, you have heard of it over and over again. You know, there is actually the pi day as well. Unfortunately, there is no E day, of course, although there should be. And also, well, this E was given in the honor of the mathematician, let me put it this way, Leonhard Euler. This is a Swiss mathematician. He led basically he put the foundations of mathematics. Well, that's a good question. Well, unfortunately, the explanations will go beyond the class, the material of Calculus 1. In fact, you can use the derivatives to prove this. But anyway, for the moment, you just have to keep this in mind. And for example, if you plug in small numbers, let's just say not the infinity, let's just say you take 2, right? Let's say if you take 2, you'll get what? In fact, let's see, for x equals 2, you'll get 1 plus 1/2, everything to the power 2. It will be 3/2, everything squared. So this would be 9/4. And 9/4 will be 1.5, right? Something like this. Or no, 2.5, something like, right? 2.5, which will be very close to 2.71. But as you grow x, if you take x3, 4, or so on, it will get very close to 2.71. So it will be around this number. So you can see it in this way. But anyway, that's what you need to know, that the limit as x approaches infinity of 1 plus 1/x, everything to the power x is E. Anyway, we'll talk about the limits at infinity at some point, probably in the next chapter for sure. All right, now let's see, how do we change the base? For example, if we take, we'd like to see how we can change the base. So the first one is what we call the change of base formula or theorem, whatever you want to call it, right? Suppose you don't like the base you're working on and you would like to change to another base. So you were given a log in base b of x and you would like to change it to log in base another base. And let's just see an example so that you can see the picture clearer. Let's just say I want to change log in base 2 of x. I want to change it to base 3. So this will be nothing else than log in base 3 of x, right, over log in base 3 of 2. So here, what we performed was change from base 2 to base 3. Right? As you can see, look here, the base 3, the same, you see it here, and here it was base 2. So that's what we have done. Okay. All right. So that's the formula. Now, as an example, well, if you want to change to base e, right? So the base of the natural log, what you're going to do is that you will take log in base b of x will be equal to log in base e of x, so that you guys be clear here. So this is log in base e of x over log in base e of b, right? Which by what we said earlier here, you see, we denoted this, we have this guy here. We will write log in base e of x as ln of x. Right, so that's what we have here. So again, this is a very important formula, change of base. Especially when we have equations or even limits, sometimes it's better to write them in a suitable base, which we can work easier with. Okay. And you can take some other examples as well. You can play around with log in base. You can take this, for example, in fact, let me just say it. You can change to base 100 if you want. So you can have log in base 2 of x, or it will be log in base 100 of x, everything over log in base 100 of 2. You see, you keep both of them 100 here, right? So that's what you're going to remember. So you're going to have log in base b of x. So you're going to keep keep the log. So you'll put x above over b will be below, but you'll keep the same new base, which will be a or whatever base you want, right? Okay. All right. So this is the change of base formula. So now, oh, sorry, let's see an example. And I would like you to think of this example. So we would like to simplify. In fact, I will take 2 minutes just to let you think of this example. Simplify the following expression. That log in base 2 of 1 over 8 plus log in base 2 of 64. So how would you approach this? You see, you're making a little bit of a mistake there. It is log in base 2, but something else. You don't add them.
Multiply, right?
Aha, we multiply them, correct. So what we're going to do, right, we have the same base here, just look at it, you look, see, and we add them up. So we know that remember log in base b of x plus log in base b of y is log in base b of x times y. So keep that in mind. So that's what we learned, right? Let me go back, show it to you again. You see the first property? Log in base b of x plus log in base b of y is log in base b of x times y. So the same thing happens here. As you can see, I multiply them. So this is where we multiply here. This is multiplication. And now we can go further. So this will be log in base 2 of 8, right? And now what can we do here? How can we compute this guy? Log in base 2 of 8. exactly like Abdul says, we can write 8 as 2 to the power 3, as you can see. And now what? This will give us what? There was a property, it will give us 3, exactly, right? So you take this on the, you take it out, so it will be 3 times, let me write it here, log in base 2 of 2, and we know that log in base 2 of 2 will be 1, so this will be 3 times 1, which is 3. And that's the final answer, right? Is this clear for everybody, this example? So this is how we operate with this. By the way, I have a question. Did you guys do this, did you do logarithm in pre-calc or something like this? You did something like, so you did exponentials and logarithms. All right, that's good. Now, okay, now let me see another example. And now again, I would like you to think of it a bit. So log, you see, I don't even put here log, whatever it is. So probably it's base e, let's say. So it's log of x a b squared. I see. Anyway, in this class, you'll learn all the properties of the exponentials and logs, because we will have to operate with them. All right, now let's see. What about this one? So we have to simplify this. So what are you going to do here? Well, like Frank says, we subtract, right? So in other words, we have that log of quantity, let's say a minus log b, it will be log of a over b. Okay, so let's do that. As you can see, we'll do this. So the quantity, let's just say that this is the quantity capital A. This is the quantity B, capital B. So this will be capital A. This will be capital B. So we will have that log of that thing, of that ratio, will be log of x a b squared minus log of 7y cubed. And of course, now we can take care of each log and we can apply the properties of the logs. So let's do that. So we have this. Why do we have this? So what can you tell me about the first log? In fact, so we have the product there, right? And in fact, we have 3 numbers. So this will be log of x plus log of a plus log of b squared. So that will be the first, so this will be this guy here. Will be this guy here. And this guy here will be this guy here. So log of 7 times y squared will be log 7 plus log y cubed. And again, we can take care of these 2 guys here. This guy and this guy. So you see they have a squared there, so we can take the power outside. So this basically will give us that this is nothing other than just log x plus log a plus 2 log b minus log 7 minus 3 log y. Right? Is it clear for everybody, the example? So this is how we apply the properties of the log of the, well, here you can say when you have log, you can, like I said, sometimes a natural log can be expressed as log. It's written instead of ln, it's written as log. So imagine that they're the same. All right. So these are the main properties, right? Do you have any questions about this example? So it's clear for everybody. Okay, that's good. Please, like I said, and I would like to say that again, and I'll say it over and over again. Stop me at any time when you do have a question. So don't be shy. Okay. All right. Let's see another example. And this example will look like this. So, given the fact that log in base b of 9 is 2, solve this for b, find b. So let's see, how would you approach this? Let's see, Jonathan says change the base to what base? Nolan says b squared equals 9. Yes, exactly. In fact, it will be easier if we say that, you see, log in base b of 9 is 2. This means that b squared equals 9. Why is that? You see, well, usually when you have log in base a of b equals c, log in base a of b equals c, this is equivalent with saying that a to the power c equals b. So always we have that. Right? So in our case, we will have that b squared equals 9, right? So when we have b squared equals 9, therefore it will give us b is plus minus. Well, is this the final answer? That's the question. Well, the thing is that the base -3 is not okay. So the answer is no, because the base, as you remember from the natural log, has to be a positive, right? I have a question. Now I see a person twice logged in. Taylor Henderson, are you logged in twice? Or there are two different, anyway, maybe I see a person logged in twice, but anyway, so the base is has to be positive, right? So the only thing we'll keep is this guy here, right? B equals 3. So was an easy one. Let's see another one. I'd like you to solve this equation, so think about it. So Jonathan says that x-axis e to the 4th minus 3, all right. All right, let's see. So how would we approach this? You see, ln is in base e. So keep in mind that this guy here is log in base e of x plus 3. So let's see, how do we approach this? Well, this guy here will be equivalent with saying, yes, x plus 3 equals e to the power 4th. So x will be nothing else than just e to the power 4th minus 3. So that's it. Plain and simple. Right? We apply the same rule as this one here. So that's exactly what we did. Right? We say log in base e of x plus 3 equals 4. This means that x plus 3 is e to the power 4. Or x will be e to the power 4 minus 3. Anyway, easy one. Let's see another one. How do we solve this? So, how would you approach this one here? Let's see. So Abdul says, yeah. Yep. So as you can see here on the left-hand side, we have something we can operate here, this one here. So this could give me, we have the same base, so it will be log of x times x plus, of x times x plus 5. And here on the right-hand side, we have log of 5x plus 4. Well, let's see. So we see we have this, just like we said. So we are applying the basic properties of the log, but now we have log of something equals log of something. And of course, since my function log is 1 to 1, right? They have the same base, then this means that these two quantities must be equal. So we will have this. So this will imply that x squared plus 5x equals 5x plus 4. And once we have this, it's just, if you do the, this will be x squared equal minus 4 equals 0, right? And we have x, it will give us x plus minus 2. So let's see, are we sure about this? I mean, only positive indeed. So we will keep only this guy here, x equals 2, right? Because like I said, the quantity, you see we have log of x here, the quantity must be non-negative. So that's what we're keeping, x equals 2. So the solution for this equation will be nothing else than just x equals 2, right? I think it's pretty standard at this point. I think you got the picture, how to operate one, how to solve these kind of equations. And now let me veer towards something else. Let me veer towards continuous compounding of interest, because somebody asked me and I avoided to answer, where does this e come from, or that limit come from? Well, guess what? When you're trying to when the bank is trying to compute your interest, that's how they're doing it. So E is called the natural exponential base because, like I said, many important growth processes are described in terms of e to the power x. I wouldn't say it sucks. It actually it helps you. Yeah, exactly. So, for example, bankers use a procedure called continuous compounding of interest. So that's how they're computing your interest in the bank. And a compound interest is given by this formula here that you see here. That's the formula. And of course, something happens when n is large enough. So this formula, this compound interest formula, is to determine, which is given by a of t, which is this number p times 1 plus r over n, everything to the power n times t. So this guy here is to determine the amount of dollars, right? Well, over time t, that will accrue from a principal P of dollars invested for T years at the annual interest rate R compounded n times per year. So this is where the base of the natural log comes from. See, you need it for your compound of interest in the bank. All right, and now suppose that, let's see what happens when n is large enough. So suppose we want to compound continuously, right? So this means that the number of compounding periods n grows without bound. In other words, n will be large enough, so it will approach infinity. And guess what happens when with a of t? So a of t will be the limit as n approaches infinity of p times 1 plus r over n, everything to the power n times t. And we can write this in a fancy way. Well, I will write this in the following way, this limit. So as you can see here, I'm writing this in this way here, because this guy will converge to e, right? Because we said that, remember, the lim as x approaches infinity of 1 plus 1 over x, everything to the power x is e. So as you can see, in our case, x is n over r, which will converge to infinity as n approaches infinity. So this guy here, right? Let me put it k here, so that I can stick to the notation. Here it's k, right? So k will be n over r. So this will be p times this guy here will be e, the limit will be e. This will converge to e. So the final result will be p times e to the power rt. So this is how we compute the number of compounding periods, how do the compound interest. So a of t will be p times e to the power rt. Okay? And let me give you an example. I'm gonna rush through things a bit. Look at this. A deposit of 2,500 bucks is made in an account that pays an annual interest rate of 10%. Find the balance in the account at the end of 5 years if the interest is computed quarterly, monthly, and C continuously. And let's see the difference. So let's see the first one, quarterly. So again, the formula A of t is P times 1 plus R over N, everything to the power N t. So in our case, so the deposit is 2,500. R will be 10 over 100, right? So it will be 0.1, and T will be 5, right? Because it's the end of 5 years, and we know that the interest rate, which is R, is 10%. So it's 10 over 100, which is 0.1. And now let's compute this quarterly. So it will be 1/4. So N will be 4. And we just plug it in, and this is how much money we will obtain. And let's see which one is the most beneficial for us. So we will get, if the interest rate is computed quarterly, we'll get in our bank account. So we'll have $4,096.54, which is not bad. Which we well, but no bank gives you an interest rate of 10%. They're not crazy. They give you at most like, well, how much do they give you? Like 1%, not, maybe a little bit more than that. But anyway, at 10%, this is how much money you're going to get. And now let's see if it's computed monthly. If we get, so for the monthly, we get N equals 12. Well, guess what? If we compute it monthly, well, again, the only difference, so everything will stay the same. The only difference is that N will be 12. And once we plug it in and we do all the computations, right, we'll get this much money. So 4,113.27, which is a little bit more than this. And let's see continuously. So continuously means that we're going to take N as approaches infinity. Right? That's what we mean by continuously. So the same thing. So guess what? We'll get even more. So this is how you want to get. So you would like your interest compounded continuously. So if the bank, which they won't give you these options because they're not stupid, if they ask you how you want your interest compound to be computed, you say like, well, I would like continuously. They say probably no. But this is how you can apply the number E. So you see, this is one example of computing the well, no bank does that. Unfortunately, they already know this stuff. So you have to come up with something. They already know this. So they have their specialists, their actuaries, their mathematicians. They tell exactly how you're going to give them the money. Of course, the bank cannot lose money, right, with clients. It's always going to be the other way around. Well, sometimes it happens for the bank, but they go bankrupt. But do you see, this is the 3 scenarios, so you would like to go with this one here. That's your favorite scenario. So you want your interest to compound to be computed continuously, so that you will get more money in your bank account. All right, and I think I'm going to stop here. So so that's the end of chapter 2 for today. Next time we will start something new. I will start talking about the derivatives. I hope the first 2 chapters were fun for you. And I will invite you to my office hours in 10 minutes. Like I said, the link for office hours is different, so you have to go with my personal ID. All right, guys, I'll stop here. Thank you very much. Bye-bye.